Alright, so today we're going to be talking about capacitors. And when we are talking about capacitors, typically what we're doing is talking about a parallel plate capacitor. And the most basic version to think of with a parallel plate capacitor is that you've got a big sheet of some conductor, and then a sheet of an insulator, and then another sheet of a conductor. So you might say aluminum foil, and then wax paper. So this is a home-built capacitor, parallel plate capacitor, and what you end up with is a sheet of foil, here's my wax paper, and there's my other sheet of foil, and then we put more wax paper there so that when we roll it up, the two conductors don't touch. This turns out to be the important piece of a capacitor, is those two conducting plates. They are not connected at all. The symbol, the schematic circuit symbol for a conductor is two parallel lines, kind of like a battery, but of equal width. And what these represent, here's my first plate, so like the aluminum foil. Here is my insulator, and here's my other plate. So with a capacitor like this, with this parallel plate capacitor, there is no direct path of conductors that goes in one side and out the other. So there is no path of conductors within the capacitor. Keep that in mind for these next couple of questions. Okay, so what we're going to start with, I'm going to have you make a prediction for what's going to happen in this circuit. We've got a battery, and the battery is going to go to the bulb. The bulb is connected to the capacitor. The capacitor is connected to a switch, and then we're back to the battery. So it looks like a regular circuit, but we're throwing that capacitor in there. So when I close the switch, what do you think is going to happen to the bulb? Is the bulb going to light up? Is it not going to light up? Make a prediction. So think about it, make a prediction. Okay, now that you have your prediction made, and remember, making a prediction is important because that's how the learning happens. So we're going to give it a try. And I've got the setup here. Let's see what happens. Okay, so here we've got the circuit. I'm using two batteries just so it's bright enough for us to see. And we've got the two batteries. We go from the positive to the bulb, bulb to capacitor, capacitor to switch. And let's see what happens. So you keep your eye on this bulb when I close the switch. All right, it's lit. What? Oh, but wait, look, what's happening? What's happening? It's going out and now it's out. Interesting, isn't that one? Okay, isn't that cool? I bet you didn't imagine that was going to happen unless you have some knowledge of capacitors already. But what happens when we close the switch? The bulb starts out lit, kind of our standard brightness, a one battery, one bulb brightness. But starts out, and then what happened? It dimmed and dimmed and dimmed until it went out. Okay, so what's happening there? Let's figure out what's going on here. So capacitors are a kind of a strange critter because if you think about this, this is an opening in the circuit. There is a break in the path of conductors. And so if there's charge flowing that way, both the bulbs lit when it was here or when it was here. And just to test it, I'm going to say let's do the bulb. Let's do series bulb and see what happens. So I'll throw a switch in. Make your prediction for this. What's going to happen? How are the brightnesses of these two bulbs going to compare to what we saw before? Ready? Let's do it. All right. Now I've got battery to, there's my switch, to bulb, bulb to capacitor, capacitor to bulb. So I've got two series bulbs on either side of the capacitor. Let's see what happens. Whoa, barely lit. It's really hard to tell. Yeah, this one's a little bit quieter, or lower brightness. But it did start lit a little bit, dimmer than before, equally dim, and now, again, we're out. So there's my next one. Okay, now both bulbs were dimmer, And that should make sense because if we have a single battery, now it has to feed two bulbs. Two bulbs is more resistant, and so more resistance with the same voltage gives us less current. Less current means less brightness. All right, so they started out dimmer, which makes sense, and equally dim, but then they did the same thing. So we gotta figure out what's going on. What's going on with these charges that are flowing when we have a break in the circuit? How can we have charge flowing when there is literally a break in the circuit? All right, another prediction for you. Let's say I go back to that very first single bulb and a switch. Okay, we close it. We're going to close the switch. The bulb gets bright, starts bright, and then dims out to out. Now, once I have that, I'm going to leave this closed for the moment. All right, so in this situation, I'm going to say right now the bulb is out. All right, so it started bright, now it's out. What do we have happening? Okay, now I'm going to open the switch up. So open the switch, and I'm going to take that battery out. I'm going to remove the battery and just close that circuit up like that. Okay, so there's no source of voltage in this circuit anymore. What is going to happen when we close the switch? So now it's just a bulb and a capacitor and a switch. When I close the switch, what do you think is going to happen? Let's see. Okay, for this one, I have just charged up the capacitor and I'm going to pull the batteries out of the circuit. Battery's gone. And so now there's no batteries, no power source. What's going to happen to the bulb? Again, keep your eye on the bulb when I close the switch. There's no battery here. How the heck is this thing lighting? And look, it's doing the exact same thing as it did before. Starting out bright and then dimming out to zero. So even though there was no source of voltage, even though there was no power source, no voltage source, no battery, we still had the same pattern happening. The bulb started out bright and got dimmer. What the heck is going on? How is there charge flowing? One more circuit for you to predict. Okay, this one's the island circuit because in this case I got two capacitors and the bulb over here. The bulb is in a conducting island. There is no path of conductors that connects the bulb to the battery. So we're going to start with what we're going to call uncharged capacitors. So these are fresh, uncharged, nothing happening with them. I'm going to close that switch, and what's going to happen when the bulb has absolutely no connection to the battery? Make your prediction, and then we'll give it a try. Okay, and here we've got our island circuit. So what do we have here? I've got my batteries going, there's my switch. I'm going to the first capacitor, capacitor to bulb, bulb to second capacitor, back to the battery. All right, what's happening with the island circuit? So this bulb is insulated from the rest of the circuit. There is no complete conducting path that goes from this bulb to these batteries. What's going to happen? Bright and then dimming out to zero again. What the heck's going on here? So let's talk about capacitors and what they're doing. Okay, what the heck? Exactly the same thing. Bulb started bright and dimmed out. What? How is there charge flowing through this bulb when there is no way for charges to be pushed out of this battery and pushed into this bulb? All right, well, to help us explain this, I'm going to use an analogy for what a battery does. So this is a mechanical analogy for what a battery does. Here's a picture. All right, so we can talk about a battery as being like a conveyor belt for charges. And I'm going to be looking at positive charges and talking about positive charges flowing. We know that physically it is the negative charges that flow. We know it's the electrons because those are the only things that are free to move. But when we talk about conventional current, we're talking about the flow of positive charges. So battery, what it does is, if we have a positive charge pop into the negative terminal of the battery, then that charge gets grabbed onto the conveyor belt and it brings it up to the positive end of the battery. So what we end up seeing is there are a lot of positives and at the positive end, as you would expect, and a lot of missing positives or negatives at the negative terminal. Now, what is inside a hookup wire? Let's just think about a basic wire that hooks up to devices. It's made of stuff, and stuff is made of atoms. Atoms are made of protons, neutrons, electrons. So are there charges in a hookup wire to start with, or do hookup wires, are they empty to start with? What makes more sense to you? If you think about the fact that it's not an empty hose like a water hose, you know, when you screw a hose onto the tap outside and then turn it on, it takes a little while for things to go. Is that the case? Is that what happens with a hookup wire? It actually isn't, because all of this stuff is made, well, it's stuff, it's material, it's made of atoms. And so it has these charges present already. A neutral object has equal amounts of positive and negative charges. So a hookup wire, we can talk about a hookup wire as being a neutral, which means equal amounts of positives and negatives. So, so here is a situation that we've got, and we've got the battery whose job is to bring the positives up here, and then we've got a neutral hookup wire. What is happening with, let's see, what's happening with this positive charge right there? Well, there's a negative here, attracting it, there's a negative here attracting it, positive, positive, repelling. And so, you know, the different amounts of charge in this neutral hookup wire are all those pushes and pulls are balancing out. But over here, not too far away, there is a ton of positives. So what we end up seeing is this bunch of positives, this high positive pressure, you might call it, is creating a push, a repel, on our little positive charge. And that little positive charge says, I want to get away from that huge pile of positives, I'm going this way. And the charge moves. We have flow. Now that's if there's room for it to flow, right? If we have a complete circuit. If there's no room for it to flow, and if we just have an open circuit, like we stop right there, there's nowhere for it to go. And so there's no flow of charge. There's no electricity current flowing. But if we do have a closed circuit, and okay, how am I going to do a bulb? I'm just going to do this. So this is, again, all full of positives and negatives, because the hookup wires are, I don't know if I started it, yeah, this is good enough. I think you get the drift. So we got the neutral hookup wires, and so if we have a complete path of conductors with a bulb, then we've got charges that are being pushed and flowing through. Then that, you know, when that positive charge gets to here, it gets and then up the conveyor belt of the battery into here. So that's the basic idea of what's happening in just your closed one battery, one bulb circuit. Now what's going to happen with a capacitor? So let's think about that. What's going to happen a few moments later? Well, a few moments later, we've started piling up positives onto this plate, this terminal of the capacitor. So push, 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 and now what's happening with this charge? Well, it is feeling a push from the battery, pushing it that way, but now there's a bunch of positives hanging out over here. Not as many, and so not as much of a push backwards. So we still have current flowing this way, but not at the rate that it was flowing before. A few moments later, we've dumped even more charge onto the positive plate, which means that the push from all of these is even bigger. And you can kind of see, hopefully, what's going on there is at some point, these two pushes become equal. There's no more unbalanced force, unbalanced push, and the charges stop flowing. So initially, we have this huge push from all this high positive pressure on the battery. But then as we dump more and more positives here, we get higher and higher positive pressure here, which means that the force, the repelling force this way gets bigger and bigger until those forces are equal, no movement, we're in equilibrium. Now that is the flow this way. How can we have flow this way? What's going on there? Let's go back to thinking about static electricity. We know that the electric force of a charged object on another charged object, we know that force can be transmitted through an insulator, like air. You know, if you have two charged objects, they can repel each other, they can attract each other. And so the fact that there's an insulator here doesn't necessarily mean nothing's happening. That insulator is just, it's like, okay, yep, I'm gonna let that repelling force through. So let's see, I'm going to go back to an earlier stage of the capacitor. So when we start, close that switch initially, we don't have anything here, and then we end up getting a positive deposited onto the parallel plate, the positive plate. Well, what does this thing now do to this positive charge? Well, okay, even because this is all neutral, this positive charge feels an even push from everything, but now there's a little bit extra. So this charge here feels a small push. Ooh, a few moments later, we've got more, and that push gets bigger. I'm going to do it the sloppy way. And then it gets bigger and bigger and bigger until we have tons of positives here. We actually have an extremely large force, big force. So even though no charges themselves pass through the capacitor, the electrical force, the repulsive force of a positive charge on another positive charge does get passed through the insulator. And so that push gets through, this charge goes bloop, and that's how we have charge flowing in front of the capacitor and charge flowing behind the capacitor. I hope this helps make sense of what a capacitor is. I'll do a video with what I call an air capacitor to give you another analogy that might also help you make sense of this weird thing, that's a cool thing, that is a capacitor. Thanks for watching.